So our next type of reaction is what's called a single replacement or a single displacement reaction. And these involve a metal replacing a metal in a compound, a free elemental metal, or a non-metal replacing the non-metal component in a compound. It could be either one. There's a couple things with this, so make sure that you get the definition out of the book. I just want to do the basic general equation, generic form. So if we have some free element and some compound out in the universe, if, remember the metals are always listed first, if T is a metal, it might be able to bump R off of S. And so what we'd end up with now is a new compound, TS, and R would be out in the cold. So if you think about reactions as positives and negatives, okay, only something that is a metal or forms a cation can replace another metal. Only something that's an anion could replace S. Okay, so this is a free element, a different element. So the gist of this is you've got one element by itself and a compound. And you end up with a different free element by itself and a different compound. Okay. Unfortunately, we can write a lot of things on paper that aren't going to happen in real life, which is really kind of bizarre. In the instructions for this, I talk about for the balancing page on page 333 in your textbook. Here's a list of some metals and their activity. The ones at the top are the most reactive and will replace, if they're by themselves, they replace anybody below them. So silver is not very reactive, neither is mercury or copper. Hydrogen, interestingly, is in here. Of course, hydrogen is really a non-metal, but it can replace metals in compounds. Kind of weird. What this doesn't show you is that halogens also do a lot of replacing as well. So I'm going to put this in as a PDF into the day's assignments because it also has something called a solubility table that's very relatively easy to access. The instructions for the balancing say to go to R54 in your textbook. At the back of your textbook, the reference section has solubilities. S is very soluble, little s, big S is slightly, I insoluble, D it decomposes, X it can't happen. That's great, but there's also on this single PDF that I'm going to upload a set of solubility rules, and a couple of things just to keep in mind. Any negative ion, doesn't matter what it is, will always be soluble with the alkali metals, the group 1 elements. Lithium, sodium, potassium, rubidium, or cesium. They're always soluble in water. End of story. Another interesting thing, any anion is always going to be soluble with ammonium. So that's kind of convenient. One last really important one to remember, nitrate. Any nitrate, there's my dog, any nitrate with any cation is going to be soluble, even the least soluble among them, okay? There's a few other things. Most of the time, I just want to point out, silver, lead, mercury, calcium, strontium, barium, they tend to be magnesium, they tend to be pretty insoluble, okay? So you have to watch out. Almost all hydroxides except ammonium and our alkali metals are going to be not soluble or insoluble. So just something to keep in mind. Phosphates, carbonates, sulfates tend to be highly insoluble as well. Okay, so just a little FYI. One cool thing about the reactivity series, the order of the halogens is the same order on the periodic table. There's no real pattern that I've ever learned to help you other than looking at a table for the metals. But the halogens are in order. Fluorine will always replace any of the others. Iodine will never replace any of the others. Okay? All right. So what's the example I wanted to share with you, and that is the reaction, and you've seen this reaction of potassium with water. I'm going to share with you one other little bizarre trick that I think helps a lot. If you think about water as being HOH, hydrogen hydroxide, it's a lot easier to see what's going to happen when you first look at this. So potassium is a metal. It's going to form a +1 ion, right? It wants to give away its 1 valence electron. So the question is, can potassium bump hydrogen off of hydroxide? The way we figure that out is we go to our handy dandy reactivity table. We find potassium's way high. Remember, potassium lit on fire. There was so much energy released, the hydrogen gas lit on fire. So potassium's very reactive. Hydrogen's pretty low, actually. So yes, potassium can bump hydrogen. It's higher. So of course, what we're going to get is potassium with hydroxide. That's actually going to be in solution, believe it or not. And poor little hydrogen's going to be off on its own. But, there's always a but, remember, hydrogen's diatomic. So it's hydrogen gas that's going to form. That's why it lit on fire, remember? And so we've got to balance this. 2 hydrogens, 3 hydrogens, that doesn't work. 1 oxygen, 1 oxygen, well, that's not so bad. But remember, if you think about it, water as HOH, we will have 2 hydrogens if we have 2 waters, 2 free hydrogens, I should say, to make our hydrogen gas. And then we have 2 hydroxides. Well, they have to go somewhere. So that means we're going to need a 2 here. And then, of course, if we have 2 potassium hydroxides, we have to have 2 potassiums as well.